It's really great to be back here. And I have to say, it's a particular treat to be invited back. That's a real compliment. Thank you, and thank you for joining us this evening. I hope I can give you a story that you will find fascinating and also useful, as Brad said, as we go into this election season. I'll comment more about that at the end, a little bit about why the bees have an easier time of making democracy work well, an easier time than we humans do. So let's start by looking at what's going on here with the bees. We all know that democracy is a form of government in which the supreme power is vested in the people, not in some despotic leader. And more generally, though, it's not just a human thing. If you think of democracy more broadly as decision-making for a group, by the group, and not by some matriarch or alpha male or something like that, I think you can see that it really can occur, it does occur, in the natural world as well. So that's what I mean when we're talking about democracy for the bees. It's a group decision-making process. And we all know that one of the curious things about democracy is it's not perfect. It's not perfect or all wise. There's this nice quote by Winston Churchill. At least among humans, it's not perfect. On the other hand, with the right organization, democracy can be, or group decision-making can be very powerful. And this is an argument made a few years ago in this really nice book by James Surowiecki. He's the staff writer on The New Yorker, writes the financial page. And he makes the point that with the right organization, democratic groups are remarkably intelligent, often smarter than the smartest individual in the group. And why might that be? Well, it has to do with the fact that when you have a group of people, you can bring more information to the decision-making than any one individual possesses. But what I want to stress are these little words up here, right organization. And that was his message as well. If you organize the group properly, then the group can be very smart. And that begs the question, what's the right organization? Well, that's where the bees come in. They can give us some examples. And at the end of the talk, I'm going to share with you what I like to refer to as the 5 habits of highly effective hives. You might wonder, well, why democracy? There's a queen bee in a honeybee colony, isn't there? So isn't it a monarchy? Well, it turns out a queen is a mother. She's a very special bee in a bee colony. She's a mother, but she's not a ruler. She doesn't not make the decisions. In fact, in a honeybee colony, the power is vested in the workers. It's the workers that decide each day where to deploy the worker force to collect the colony's food. They're the ones that decide whether to turn the heat production up or turn it down to maintain the temperature in the hive. They're the ones that decide, do we need more water or not, etc. So it really is appropriate, even though there's a queen, so-called queen in a colony, to look at a beehive as a democratic unit. And the story I'm going to tell you about is democratic decision-making in one particular context. It's in the context of a swarm of bees that is choosing a home. Here is a swarm of bees. What is a swarm of bees? First of all, it's a reproductive propagule. It is a group consisting of one queen bee and 10,000 worker bees, thereabouts. They have split themselves off from an existing hive, and they're set out to establish a new hive. Meanwhile, back in the original hive, new queen bees are being reared. One of those will inherit the existing hive and will inherit the workers that stay at home as well as the established nest. So these bees have left. This happens in the late spring, early summer. It's like an amoeba fissioning in itself. Part leaves, part stays. They leave their hive suddenly on a nice sunny day, but they haven't yet chosen where their new home is going to be. So they don't fly very far. They might fly about 100 feet. Then they coalesce in this beard-like cluster hanging from a tree branch or a stop sign, wherever they cluster. And here they have to find their home. And this is going to be a life or death decision to them, because honeybees need a very protective nesting cavity. To get through the winter, a honeybee colony survives winter by forming a tightly insulated ball of bees, and they're making heat all winter long. Inside a beehive, there's a cluster of bees all winter long. The inside of that cluster is kept about 95 degrees Fahrenheit, really toasty and warm. But that only works partly because they have a lot of honey, which is their fuel for heating that, but it also requires that they have good shelter. They can't have cold air blowing past them. They would burn through their honey too quickly. So it's a life or death decision to find a good home. How do they do it? Well, the starting point is that they have a search committee. Of these 10,000 bees, they have it's a small percentage, but it's still a large group of 300 to 500 bees that are going to be responsible for choosing the new home. We'll call these scout bees. And they start the whole process. They do it by flying off this cluster, fanning out. Each one is searching on her own, fanning out, or going in all different directions around the countryside, and looking for potential home sites. These would be cavities in trees or in buildings. And once the individuals have found something, they will come back to the swarm. They'll report their discoveries, because one bee will find something over here, and another over here, and another over here, and another over here. And now they will conduct a debate, as we'll see. And they will work through their debate, and it can take a few hours or a few days, but they will, by pooling their knowledge and holding the debate, they will identify the best cavity that's been found, and they'll move to it. Now, what are they looking for? Well, I want to illustrate a dream home for honeybees, and I'll do it with this sugar maple, which is up in the woods, was up in the woods behind my house. What makes this a dream home for the bees are a couple of features about the entrance and the cavity. They want an entrance that's high off the ground, so that things like bears are unlikely to discover the nest. They want a small entrance, so there's not cold air blowing into the entrance during the winter. They need a spacious cavity, one that's about 40 liters or about 10 gallons, so they have enough room in that cavity to build the combs they need for rearing bees and storing honey. And ideally, they'll find all of these things in a live tree. And I think you can see this is a rather special combination of traits. You have to have a live tree that has a big rotted space inside it, and yet that large space is accessed through just a small entrance. And to boot, that little entrance is high off the ground. And that's a combination that's not easy to find, and that's probably why they deploy several hundred scouts to go searching. Most of those several hundred scouts, only about a dozen or so, actually find a possible home site. So they search far and wide, and that's what they're looking for. When a scout bee comes across a potential home site, she'll first make a private evaluation of the site. You can see these scout bees in the spring going up and down trees, and if they find a crack in the tree or a knothole, they'll go inside. And if she finds one that's promising, a scout will spend about a half an hour making a couple of dozen trips inside the cavity, where she walks around on the walls inside the cavity, such as this scout bee did checking out an experimental nest box. She'll walk around making multiple visits inside, and over that half hour or so she's spent going inside and inspecting it, she'll get a good sense of the volume of the cavity, the entrance size, and the other things that matter to her. And in ways that remain a mystery, the little bee is able to combine her knowledge about these different features of that site into a sense of the overall goodness of that site. It's like she puts it on a scale of 1 to 10, 10 being tops. She'll now come back to the swarm cluster and make a public report on the surface of the swarm of what she's discovered. And here she's going to tell the other scout bees that were not successful in finding a potential home site the direction and the distance and the quality of what she's discovered. This is remarkable. This is being done by a little insect. And the way she shares her knowledge is she performs a dance. It's called the waggle dance. It's a behavior where the bee walks forward on the surface, the vertical side of the comb. She'll be walking forward, waggling her body back and forth to make herself conspicuous. And she'll do that for a certain period of time. Then she'll stop, she'll come around, and she'll do that again and come around again. I'll show you a video of this behavior. It's really quite eye-catching. What we're going to see is a bee. She's going to appear right about here, and she's going to be, first of all, she's dancing, you'll see her dancing on the backs of the quiescent bees, that other 95 to 97% of the bees in the swarm that are not scout bees. They're hanging out for a few days in that cluster. She's going to dance on the back of them. This is a side view, so we're looking at this vertical surface of the swarm, and you'll see a waggle dancer in here. Here's our dancer. She waggles, stops, comes around, waggles, stops, comes around. Notice every time as she does this waggling, she's pointing in pretty consistently in this direction. It's about 90 degrees to the left of straight up. And each waggle lasts about the same amount of time. It's about a little over a second. 1,001, 1,000. And you'll notice other bees that are tagging along behind her. Those are the other scout bees getting the information from her. And she's indicating the location with the waggle dance in the following way. She's indicating the direction by the angle with respect to straight up in which she walks as she waggles. So for example, let's say we're looking at a bee that's not a scout bee, but a forager bee. Let's say she's living in her nest, her colony lives in this tree, and she's found a patch of flowers that's rich in nectar or pollen. She wants to share that information. What she does is when she comes back to the hive, she notes the direction of the flowers relative to the direction to the sun, the projection of the sun to the horizon. In this case, that would be 40 degrees to the right of the direction to the sun. When she gets back in the nest, and inside the nest, she can't see the sun, she reproduces that angle of 40 degrees to the right, but now it's 40 degrees to the right of vertical. It's as if she imagines the sun is straight up on this vertical surface. And so but she indicates the direction of the flowers by that angle, and the bees following her can read that angle. And she indicates the distance by how long each of these waggle runs lasts. So if the greater the distance, the longer the duration of the waggle run. And it's remarkable and you can see that this communication system works over thousands and thousands of meters. That can be up to miles from the hive. And it's one of the great wonders in the animal world that these little insects can perform a dance inside a hive or on a swarm to tell other bees about the location of something important that can be miles away. It was deciphered by an Austrian zoologist at the end of World War II. This was gentleman, Karl von Frisch. He investigated this and he worked it all out in the context of bees communicating the locations of rich food sources. He did not know initially that bees also use the same communication system in the house hunting process to communicate about nest sites. It was one of his students that worked this out, a gentleman named Martin Lindauer. He was a postdoc working with von Frisch at the University of Munich in 1949. And what happened is he came out of the institute, the Zoological Institute, one day, noticed that there was a swarm of bees hanging from a bush near the entrance from one of the hives at the institute. And he noticed first that bees were doing these waggle dances on the side of the swarm. And he thought at first, okay, well, that's interesting. These swarm bees must be hungry, and they're still collecting food. But Lindauer was a very good observer, and he noticed that there was a couple things that were odd about these bees. One was, the most oddest thing is these bees were kind of dirty. Some of them had what looked like red, they were red with brick dust, and others were black with soot. And he said he plucked one of these bees off, one of the sooty-looking ones, and he sniffed it, and he said it smelled like a chimney sweep. And that was his first clue that these bees were certainly not coming back from flowers and were probably scout bees that were reporting on potential home sites. Now, why were bees coming back with brick dust and soot? It's because the year was 1949. Munich had been heavily bombed during the war. These little scout bees were going out finding cavities in bombed out chimneys and broken buildings. And that's why they came back so dirty. I like to think they invented dirty dancing. Now, Lindauer had also the wisdom and the insight to realize, I can read these dances that these probable scout bees are doing, And I'm going to do that. I'm going to sit by one of these swarms, and just from dawn to dusk, I'm going to record as much information about these from these dancing bees as I can obtain. Because for each dancer, he could determine the distance and direction of what she's indicating. And when he did this, he found some very interesting things. He found that initially the bees on the side of the swarms would perform dances for multiple sites all around the city. But after a few hours or a few days, however long it takes the bees to make their decision, the swarm flies off to its new home. Before that happens, before they launch into flight and move off to their new home, all of the bees performing dances are indicating just one location. And then he was able to determine that the swarm, when it flies away, it flies to this site, this dance consensus site, and moves in there. And he was able to do this because when a swarm takes off, it doesn't fly very high, and it doesn't fly very fast. It gets its top speed is about 5 miles per hour, so he could run along beneath the swarm. And this is a map he had to depict his tracks. His first swarm flew to the north, 1 block, 2 blocks, 3 blocks, 4 blocks, and moved into a broken wall that was here. And that was the location that the dances had all indicated right before the swarm flew to its new home. So he was able to conclude that these dances on a swarm do indicate possible home sites. And he also had the really nice insight that bees, he didn't call it democratic, he called it a plebiscite, but the idea was he had the insight that they had a democratic method of choosing a home. Because he even did things like he took the queen out and put her in a little cage so he could control where the swarm clustered. And he could see that she didn't have to be in physical contact with the whole process for them to choose their home. And he saw that there were hundreds of scout bees involved. So he thought it was democratic. But what he was never able to work out is exactly what the democratic process was. He saw that they started out with a variety of opinions and ended up with one agreement about where they'd live, but he didn't work out how it worked. And the reason is, I talked to him about this, he said this was the most beautiful discovery of his life, and I would have to agree with him. So I asked him, why didn't you pursue it more deeply? And he said, well, I didn't really have many resources. The only tools he had, this was right after World War II, the German economy was still in shambles. He had a chair, he had a pencil, he had a notebook, he had a little paint set for labeling, putting paint dots on the bees, and he had a stopwatch, and a wristwatch so he could know the time of day and he could time the dances. And he said he was very limited. He could only really take a little bit of data. He couldn't get a comprehensive view of what was going on. And he published his work on this in 1955, and that's where the story sat. It was like a real mystery. And in 1997, about 40 years later, I decided to take up this mystery. And what I did to begin with was to really pick up where he left off, just to make a detailed eavesdropping on a scout bee's debate. Whenever you study animal behavior, almost always a critical first step is just to see what the animal is doing, not experiment, just observe. And I had 40 years after Lindauer, of course, we have video recording. We have little license plates that we can glue on the backs of bees. I would make swarms, 4,000 bees, swarms, relatively small swarms, manageable ones, where every bee is labeled for individual identification. This bee has a little orange paint mark on the abdomen, so she's orange, red, 3. And over here, I can't read all of these colors, but here's somebody that's yellow, 6, and so forth. And it doesn't, if you have a nice team of undergraduate students that'll help you label the bees, you can get all 4,000 bees labeled in a day. And I like to say that when you've got this, each of these bees suddenly becomes fascinating. She's an individual. She's not just Apis mellifera anymore. She's orange, red, 3. And she does interesting things. And what I would do is I'd have that swarm, and I'd have the queen in a little cage, and wherever you put the caged queen, the beekeepers here know this, wherever you put that caged queen, the worker bees in the swarm will cluster around her. So I could mount the swarm on a board and video record everything that happened on that swarm, all of the dances by the scout bees. And when you do this, you can get a complete record of every dance, that is to say, every dance that's done. You know which individual did it, you know when it was done, and you know what location the bee was advertising with her dance. And I want to walk you through one swarm's debate. This unfolded over 16 hours. That it took 3 days. It started midday on the 20th of July, and it ended on the 22nd of July, also around midday. And it involved, in this particular decision-making process, they considered 11 possible home sites, and there were 149 scout bees involved in performing dances as part of the decision-making. Now, this is the most important slide of the talk, so I'm going to walk you through it carefully. Each of these rectangles is a depiction of the pattern of dancing for typically a 2-hour time period. So here we go from 11 a.m. to 1 p.m. The circle depicts the location of the swarm, depicts the swarm. Each of these arrows depicts the amount of dancing for a particular nest site. Now, the direction of the arrow points in the compass direction of the site. So this pink arrow denotes dances for a site that was to the east. And the length of the arrow indicates how far from the swarm that site was. Here's a distance scale down here. So it was about the site to the east was about 2 kilometers away. And the width of the arrow indicates how many bees during that 2-hour time period performed a dance for that site to the east. And here's a scale to convert from arrow width to number of bees. So this pink arrow tells us that during the first 2-hour time period, there were about 10 different scout bees that performed a dance to advertise that site to the east. Now, how do you get 10 bees? It started out with one scout bee that discovered that site. She came back and did a dance. Other scout bees followed her dance. They went to that site themselves. They checked it out for themselves, and they agreed with her that that was a good site. So they came back and they added to the report on that site by performing their own dances. And you can see that there were other sites during that first 2-hour time period that were also discovered and were also reported. They were not as popular as Site A, however. Now, what happens during the next 2-hour time period, 1 to 3? Well, again, it's much like this. A variety of sites are being advertised by scout bees. And as you can see, they're in different directions and different distances. And here, same sort of thing. Getting to the end of the afternoon, a variety of sites were being reported by scout bees. And here we are, 5 to 7 p.m. on the end of the first day. Still a variety of sites are being reported by scout bees, but notice the site to the south, B, and the site to the southwest, G, are getting most of the action. They've attracted most of the dance activity. But still no agreement. The next morning, things start up pretty much where they left off. The site to the south and the one to the southwest are getting most of the advertising, most of the interest of the scout bees. And you can see little by little on this 21st of July, Site G starts to climb ahead to Site B to the south. And Site G almost became the unanimous choice by the end of the morning, but then it started, but not quite, and then it started raining, and the whole process shut down. Bees don't fly in the rain. The next morning it was sunny, and the next morning there were 73 different scout bees that performed a dance for a site to the south, this site to the southwest, and that was the only site that was advertised. And at 11:58, the swarm flew away and flew to the southwest to that chosen site. So isn't this remarkable? These little insects have gone out, found a variety of possible places to live, and winnowed it down to just one site. They've built an agreement. They've reached a consensus. That's remarkable. What's even more remarkable is that site they chose wasn't just any one of the sites. It was the best site. So they're not just making a decision, they're making a good decision. Now, how do I know that they chose the best site? I don't know it from this particular experiment. I know it from another experiment where I actually test their decision-making ability. And to do this, I had to leave my bee lab at Cornell University and go out to Appledore Island, Maine, which is where Cornell has its Shoals Marine Laboratory. It's a teaching laboratory for undergraduates. And it's on an island, Appledore Island. It's 90 acres. It's 6 miles out in the Atlantic. And it's a perfect laboratory for studying house hunting by honeybees, because on this island, I control the real estate market. Now, why is that? Well, this island has no big trees on it. It was grazed heavily in the 1800s. It's slowly coming back through succession, but it's covered with brush now. So I could take a swarm of bees out to this island, and those bees are stuck. They're going to have to look at the experimental nest boxes that I'm going to provide. The mainland's way back here, but it's 6 miles across the open ocean. That's too far for the bees to go. So they're stuck on this 90-acre island. So my plan was, okay, I'm going to give them a multiple choice test. I'm going to put a swarm at the center of the island on a porch of one of the buildings, and out over here in this fan-shaped array, I'm going to put out 5 possible home sites. One of them is going to be excellent. It's going to be a 40-liter box. You remember that's the size they like. That's a model home. And the other 4 are going to be okay. They're going to be acceptable, but not as good as the one. They're only going to be 15 liters, and this just shows the design of these experimental nest boxes with an inner wall that can be put in different locations to adjust the volume of the box. So the plan was, put out these boxes, set up a swarm, and see how well the swarm could find all of the boxes and choose the best one. And this is what one of these boxes looks like. Each one is in a little orange hut, so they're all sheltered from the sun. They all face the same direction. The only way they differed was their volume. So that's what I mean. I had good control of the alternatives. And I was very excited when I did this experiment. Because I got out to this island, I thought, wow, this is dynamite. Cornell has an island where I can do this experiment. So I go out there with a swarm of bees. I set up the nest boxes. As you can see, I'm waiting at the boxes here, waiting at one of these boxes for the scout bees to arrive, but no bees arrive. And so I waited about an hour, and I thought, what's going on here? What's happening? Why isn't this working? So I went back to the swarm. The swarm was here, and to check out whether they were doing any dances. And indeed, the scout bees were dancing to beat the band. But they were not in, and I quickly read the dances, and it was immediately clear. They were not obviously going over in this direction. They were going over in the opposite direction to a little house that was over here. And that was not good news, because I was told to never go to those houses over here. Cornell leases this island, and it doesn't lease the whole island. It doesn't lease these private residences. And I particularly was told, don't go to that house. There's one house over there you should never go to. Now, what's with that house? Well, this is where Rodney Sullivan, a lobster fisherman, lives. He's quite protective of his place. He keeps a loaded shotgun behind his door. And if anybody comes poking around his place, as he likes to say, I don't cotton to people poking around my place. He was known to fire it off. But my scout bees didn't know anything about that, and they discovered his chimney, kind of like Lindauer's bees. And they thought that was good. I mean, it was pretty good. It was a good place on this island, which doesn't have trees. So I went to the director of the lab and I said, Jack, I think I got a problem. We're going to have to, I was told not to go to that house, but I think my bees are going over near that house. I think I need to go over there. And he said, well, go over there, but don't go by land. You can't sneak. He'll think you're sneaking up on him. Get in a boat, go around, and call up to him. And I did that, called up, and he was happy to, he said, come on right up, and because he said, I got a problem with bees. Never seen anything like it before. And he was happy to see me. Not that he knew immediately that I was the source of the problem, but I told him I could help him out. So the solution was quite easy. Just he built a fire, smoked out the bees. We put screen over the top of the chimney. And now the bees were really under my control. And now they did start showing up at the nest boxes. And this is just an illustration of the results. These are plots that show for across the time of the day for each of the nest boxes how many scout bees are visible outside the box. That's a measure of how much interest they have in each box. And you can see on the first trial with the first swarm, they found all of the boxes. And they started getting interested in this one, but they eventually built up their most of the interest there, the good one, and chose that. In the next trial, the same sort of general pattern happened. They started getting interested in some of these other boxes, but as soon as they found the really good one, the numbers shot up there, and they chose that. And we've done this experiment many, many, many times, and they get it right about 95% of the time. So they're good at making, that's what I mean when they say they make a good decision. But how do they actually make these decisions? How do they make these democratic choices? We have really only looked so far at the pattern, not at the process. Well, we're going to have to answer two questions. We're going to have to answer the question of the bee's interest grows and grows for the best site, but how does that happen? Look back at this diagram. It started out, this winning site started out being represented by only 13% of the dancing bees, and then it grew to 33%, and then 62%, and finally 100%. So something happened where interest grew and grew for that site. And at the same time, the bees' interest faded for all the other sites, the poorer sites. They all faded away. Even this site to the south, which actually attracted a lot of interest by the scout bees initially, or partway through, it was all gone by the end. How did that happen? Well, one way to think of this, and it's appropriate, we're thinking about this now, is that they conduct a popularity contest. They hold a democratic election when you think about it. Because what is a democratic election but a popularity contest? And you have, in the case of the bees, like we are looking at with our presidential election right now, you've got different candidates. In the case of the bees, they happen to be hollow trees instead of, well, I shouldn't say, hollow trees. Site A and Site B. You've got supporters for each of these sites. The scouts that have found Site A and are excited about it, and scouts that have found Site B and are excited about it. And they're trying, doing their best to attract the uncommitted voters, the uncommitted scouts, to join their group by, in this case, by performing these dances, which are like advertisements for their site. And a key feature that this whole, so it's really a competition. It's a tug of war for these uncommitted voters here. And a key thing that makes this work is honest advertising of the candidates. In the bees, a site only gets strong advertisements, i.e. strong waggle dances, if the site is really good. Even though these scout bees for Site A are for Site A and these bees over here are for Site B, they don't have bedrock differences. They all are in the same boat together. They all want the swarm to choose the best home site. And so there's no incentive for these bees to lie or be dishonest. If Site B is not so good, the bees will not dance for it with strong dances. You might wonder, how do we know they're honest? Well, it's not hard. We went back to Appledore Island, did a simpler experiment, put out 2 nest boxes, one high value, 40 liters, one medium value, 15 liters, had scout bees coming back to the same swarm at the same time, but some were coming back from the high value site and some were coming back from the medium value site. We video recorded the dances, and the key thing we checked was how many dance circuits each scout bee produced to advertise her site. And these are the distributions we got. So here we've got the total number of dance circuits produced by a scout bee, and here's the distribution for the dream home, and here's the distribution for the fixer-upper. On average, there's a lot of scatter, but on average, a dream home scout bee coming back from the dream home performed 90 dance circuits. That takes several minutes. On average, a bee coming back from the fixer-upper only did 30 dance circuits. That takes only about a minute. And if one dance is 1 minute and another dance is 3 minutes, there are a lot more scout bees that can, 3 times as many in fact, that can follow the dance and get the information from the dream home dancers than from the fixer-upper dancers. So that biases the recruitment and the popularity, the buildup of popularity in favor of the better site. Oh, and I should point out that this implies that these scout bees know innately what makes a good home. Because these bees have never been scout bees before. This has to be the rule of evaluating a site and translating that into a dance of a given length has to be built into the bees. So they have an innate knowledge. So we can look at this choice process through these diagrams here. And it's a key part of it is honest, accurate campaigning. So if you have two sites, let's say there are just two sites, the simple situation. One's good, but one's excellent. And let's say they're both discovered at the very same time by one scout bee each. So this bee representing this site does 3 times as many dance circuits for the excellent site as this one bee for the good site. If you came back a few hours later, lo and behold, there'd be 3 times as many scout bees now dancing for the excellent site than for the good site. And each of these, not only are there 3 times as many bees now, but each of these bees is still doing 3 times as many dance circuits as the red bees. So if you came back 3 hours later, the pattern of dancing is biased even more in favor of the excellent site. And one thing I should say is that not only are the dances building up in favor of the excellent site on the swarm, but a scout bee, not only to show her support for a site, not only performs dances for that site, but she then goes and spends time at the site. In fact, turns out it's spending the time at the site, which is really how a bee is a very important part of voting in favor of that site. Because we didn't know this for a while, but we now know that a site wins in this contest by being the one that first attracts a quorum, or a critical threshold number of scout bees. And what happens is, so a scout goes to a site, typically she's recruited to that site, she checks it out herself, she comes back and does a dance for that site, but then she goes and spends time at the site. And when she's back at that site, she can look around and see, are there a lot of other bees here yet? And if there are, she will, if it reaches this quorum level, the scouts from that site will come back to the swarm. They'll trigger all those quiescent bees to launch into flight through a process I don't have time to talk about tonight. And once they've triggered the swarm to take off, the bees from this site will guide the bees to that site. And that's how they actually implement their decision. But that's a whole nother story. I want to quickly go into this other question, though, about the bees' interests fading for all the poorer sites. And that's, in some ways, that's even the most remarkable part of this whole process. And it's something we've just learned about in the last couple of summers about how they actually do this. All these bees, even the bees for the south, all stop dancing by the end. How did that happen? So the question is, how does a scout bee lose interest in a site? One thing we've learned quickly by tracking these individually labeled bees is that scout bees are not doing comparison shopping. It wasn't the case, for example, that these bees that were enthusiastic at one point for the site to the south walked around on the surface of the swarm and saw even more bees doing more enthusiastic dances than their own for the site to the southwest. That's not what goes on. These bees don't do comparisons. In fact, each scout bee, during her activity, goes to one site, inspects it, comes back and reports on it, and doesn't pay attention to the dances of other bees. She doesn't shop around. So it's not a matter of comparison shopping. But what does cause a bee to lose interest in a site? They are encouraged to drop out. Now, how does that work? Well, it works the following way. The scouts from the different sites actually inhibit one another from continuing to be excited about their site. And they do this by producing what are called stop signals. I'm going to show you a video of one, but let me say it in words first. What happens is a scout bee, she's come back from her site. She's pretty excited about her site, for example, or she's excited at the appropriate level, and she'll perform waggle dances for her site. But not only does she advertise, not only does she make these excitatory signals about her site, but she'll take some time out and walk around on the swarm. She's not doing comparison shopping, but she is looking for bees doing dances for other sites. And if she finds a bee doing a dance for another site, she will come up and she'll butt against that bee with her head, and she'll hit on the dancing bee, usually in the shoulders or the head region, while she makes a little beep sound. And that beep sound is in there, I think, to add emphasis to that head butting, to tell that bee, this isn't just an incidental butt, this is a real signal that's saying to you, slow down your dancing, reconsider what you're doing. And so the sender butts the dancer with her head. Now we'll look at a video of this. And what you're going to see is this bee here, she's got a blue and yellow paint mark on her. She's going to be doing a waggle dance, and that paint tells us that she's coming from one site. This is from an experiment on Appledore Island. We had 2 sites set up, and what we're going to see is a bee coming back from the other nest box with a pink paint mark. She's going to come in from the top. She's going to walk down. She's going to butt this bee. And you'll hear the sound. Here she comes. 1, 2. Well, I'm going to play that again. My computer's a little slow. Here's our dancer. 1, 2. Three. Now, we just discovered this in 2010. Nobody knew the bees had this signal. It's a very soft sound. It sounds loud to us because there's a microphone right next to the dancing bee here. And we know, I don't have time to go into the details, but each time the bee gets butted, it's like a little dose of inhibition. It's like cool it. It's like saying cool it a little bit, cool it. And this means that if we go back to this diagram, these red bees are losing in the competition, not only because they're being out, their excitatory signals are not as strong as the blues' excitatory signals, the waggle dances, but now they're really getting hammered by these stop signals from the blue bees. It's a kind of way of, it amplifies the difference in the strength of the difference in the buildup of popularity for the 2 sites. And we think that this stop signal, one of its main functions is it reduces the chances of a swarm ending up in a stalemate. Because it means that even if the bees had found 2 sites of identical quality, as soon as one site gets a little bit ahead, just by chance, the whole system is biased to favor that site. So they avoid a stalemate. Well, this brings us back to this part about with the right organization. What lessons can we learn from the bees now that we know something about how they make their decision? With this main idea is that with the right organization, democratic groups are remarkably intelligent. So what is the right organization? Let's look at these 5 habits. And I'll walk you through these, and they're what for me makes a swarm a fairly brainy thing, but I have used these I use these in faculty meetings in my department. And those of you that are academicians might know that faculty meetings can be characterized as hornets' nests. I'd like to think that with these rules, which I've learned from the bees, it can make it more like a beehive. So 5 habits. One is the group members. 5 habits of a really effective decision-making group is a situation where the group members focus on their shared interests. And this is what we see with the scouts. They work together for a common good. And you might think that's impossible to do. Sometimes it is very difficult, but often reminding people that they do have as many common interests as they have difference, or shared interests as differences, can set the right tone. Second habit is the group members possess an impartial leader, a moderator, not somebody who's a proselytizer, but somebody who sets the right tone for the discussion and the debate. And in fact, the bees take that to the extreme. They have no leader. They don't even have a moderator. The third habit that I've learned from the bees is to have the group members start their decision making by seeking diverse solutions to the problems. We see this with the scout bees. They fly out, they find and report on a broad array of potential home sites. And in a tough decision, this good starting with a human group, a good way to start is to say, okay, let's get the options on the table. Just go around the room, get everybody's suggestions. Not try to sort them out initially, but just get them on the table. A fourth rule or habit that I've learned from the bees is to have the group members avoid a tendency to seek a rapid consensus. Give the group time to argue the matter through carefully. Because really, somebody can propose one idea, somebody else can say, I don't understand that, I don't believe it, here's why. And little by little, just airing these differences, clarifying the differences is very powerful. And not every group is comfortable with argument, and it doesn't have to be a nasty argument, but it's important to chew it, to kick things around. And we saw that with the Scouts. They conducted vigorous debate to identify a winner. And the fifth rule, or habit, is that if the group members can balance interdependence and independence. And what I mean by interdependence is I mean sharing information, communicating, so that ideas that are in one individual's mind can percolate within the group, through the group. But also to be independent. That is to say, have individuals learn about what ideas other people have and their thoughts, but in the end to make their own independent judgments. And we see that with the Scouts. They hold a public discussion where with their waggle dances, they share information about the possibilities, but they really rely on their private evaluations. A bee will go to a site. A bee will vote for a site. She'll go to a site. She'll come back and dance for the site, and then she'll go back to the site, but only if that site meets her own evaluation. Or we've never seen it, for example, a bee get excited about a site and dance for a site simply by following another bee's dance. No scout bee takes another scout bee's word for it. She learns about the site from a scout bee, but she will only advertise it herself and keep visiting it based on her own evaluation. And that's very, very important. And that would be done in a human group situation if it's really sticky by having secret ballots, so nobody feels they're being influenced by others. So that's normally where I end this talk. But since it's the election season, I thought I would actually also say a little bit about some thoughts about what advantages the bees have over humans, just to put our own situation in perspective now that we've looked at the bees. Well, one thing that helps the bees is they, of course, face a far simpler decision-making task. All they have to do is find a hollow tree that's the right kind. What do we have to do? We have to make a choice between individuals based on what their plans and preferences are for a wide array of things. Health care, the state of the military, the state of the budget, the spending, all these very complicated issues. So we have a much more complicated choice than the bees, much more complicated decision-making task. Another thing that the advantage the bees have is that the bees rely on evidence, not emotion. And especially what we're seeing in our own campaign now is huge amount of fear-mongering. And that's not evidence. That's really tapping into people's fear about everything. And that's not the way the bees do it. They're really reporting, okay, I found this site, I evaluated it to this level of goodness, I will dance to this degree. It's a very different way of doing it. It's almost like the bees are scientists and not politicians. Another feature that the bees have is they're honest. I would have, you may not agree with me, but I would just using this as an example. There's no Fox News, and they don't need fact checkers to find out, to clarify what's true and what's not true. And the bees don't have any demagogues. There's no individual in that bee swarm that is triggering often emotional thoughts, making claims that are grandiose and promising to do things like cut all sorts of things like cut the taxes, erase the deficit, create jobs, bolster the military, block abortions, and all at no cost to you. There's nobody in a swarm that's doing anything like that. So I think you can see the bees have a number of advantages over ourselves. And it's partly why we have many more difficulties. We have a much more complicated situation. But you may not like what I've just said, so I'll end on a slightly different note. I'll just invoke the bard. And I think he had it right when he wrote, "For so work the honeybees, creatures that by a rule in nature teach the active order to a peopled kingdom." Thank you very much. If this work on Appledore Island intrigues you, I'm happy to share with you that Nova Science Now, we worked this last summer reproducing many of the experiments I've done, filmed that, and it's going to be part of the Nova Science Now program on PBS television on November 7th at 10 p.m. So if you enjoy it, can see it for real there. How are we doing for time? I'd be happy to do questions, whatever is appropriate.
How consistent are the dances? If they go out the first time and they discover Site B, and they come back and they dance to indicate the direction and the favorability, I guess,
Right.
of the site, and then they maybe go back to Site B again, unless they saw somebody dance longer and more poignantly for Site C or something.
Or if they've gotten beeped a lot.
And
Yeah.
but and when they come back, do they have then exactly the same dance that they had
Yeah.
the first time they came back?
Yeah, the dance will be, the precision of the dance is quite high. It's within about plus or minus 3 degrees. And so yeah, they are able to nail that direction, that location quite precisely, time after time after time. And you're right, a bee will go to a site, inspect it, come back and dance for it, and then she'll go back to the site to check to see if a quorum is formed there and to contribute a vote for that site. And if she still likes the site and she hasn't gotten beeped too much, the next time she comes, she'll come back to the swarm and perform a dance again. But again, she's nailing that location.
In the same direction, but also the same intensity? In terms of the quality?
Generally, the intensity is dropping away because when they come back, usually they're getting beeped, and so they're getting these doses of inhibition, and their dancing is starting to drop down. But it starts so much higher if the bee's coming back from a better site that she will keep dancing longer than a bee coming back from only a mediocre site. Yes. Oh, okay. Yeah.
I have two questions. One, I didn't realize that the queen could fly. Does the
Yeah.
queen fly?
Yeah, the queen is a flyer. She's not a strong flyer, but she does fly along with the bees to get to the new home.
Okay. And then my second question is, I'm wondering if all of the bees in the swarm participate in the decision or if they have like delegates.
It's just the scout bees. It's just that 3 to 5% that you can think of them as representatives. It turns out these are the oldest and most experienced bees in the swarm. The bees with the most experience flying out across the countryside and then finding their way back to the hive. They had been foragers before they were scout bees. So it's just about 5% of the bees.
So then how do the scouts communicate to the rest of the
Yeah,
bees?
I didn't get to, yeah, thank you for that question. I didn't get into that. What the scouts do, the scouts from the winning site, once they've sensed a quorum is built up at their site, they come back to the swarm, they make another signal, which I didn't show. It's called the worker piping signal. And they go around, they grab the cool quiescent bees on the swarm, they push their thorax against that, each of these scouts will push their thorax against the quiescent bees, make a little sound that sounds like this. Zzz, zzz, and that tells the bee, the decision's been reached, it's time to get ready to fly. You need to warm up your flight muscles. They have to get their flight muscles about 90 degrees Fahrenheit for the flight muscles to work fast enough to support flight. And then once they're doing the piping, and that takes about an hour to get everybody warmed up. And once they sense that everybody's warmed up, then they do a buzz run, another signal, which is a bee running around through the swarm. One of these scout bees from the winning site runs through bulldozes through the other bees while buzzing her wings, and that's the signal that says, let's go. And that tells them to launch into flight. And then to steer the bees, because it's only about 100 or so bees that know about where the swarm should go, the bees from the winning site. They steer this swirling cloud of bees to the new home site by zooming through the cloud in the direction of the new home site very quickly, so they're conspicuous. And then when they get to the front of the cloud, they slow down and come back and then zoom through again. So they're pointing the way. That's a whole story in itself. But thank you for asking that question.
In your example where you had the blue and the red
Yeah.
bees, do the red ones that are getting outnumbered and so on, do they change their mind and convert to the other, or do they just continue being loyal to the site they found first?
They will not, very few bees will switch. It's less than 10% of the scout bees that have that ever change their mind. What we see almost always is the bees just, they've done their thing, they've made their vote, they've made their trips to the site that they voted for, and then they just let the chips fall. They drop out and they pass the decision-making on to the rest of the scouts, the younger scouts that take up the process. It's a little different than the way we would hold the discussion.
So you had a chart up there that was displaying the dance circuits that the bees were making to show their excitement about a particular location. And I was noticing that for the fixer-upper, which is, almost half the size, you still have some bees that are really excited on the one end, and with the dream home, there are some bees that don't seem all that excited. So I'm wondering, is that a lack of thoroughness when they search it, or is that the result of the stop signals, or are there just some stupid bees that aren't good judges of quality?
It's really hard to say. Your point's well taken that there's the coding or the expression of information about goodness by these bees is very noisy. Yeah, you've got a lot of scatter in both of these distributions. I don't know where that scatter comes from. Some of it is because, yes, there were some of these bees that were dancing for the fixer-upper that were probably getting hammered by the beeps by the time they got to their dancing. But that can't be the whole story, and I think there's just a lot of noise in the system, and it may not be that evolution hasn't trimmed out this noise because the whole system works on averaging. I didn't stress that point, but it doesn't require that each bee get it exactly right, but just on average, because you've got hundreds of bees involved here.
So it's difficult to say why that dot on the far right of the fixer-upper, that bee that's close to 200, is so excited about the 15-liter.
We do know from our studies in the context of foraging, you can have 20 bees going to the exact same feeder at the exact same time, and of those 20 bees, some will be very excited and some will do no dances at all. And when we do those experiments, we actually usually remove the lousy dancers if we're trying to get data on the dance pattern. Where that comes from, we don't know.